Portal number 17, the Black-Scholes option pricing model. Black-Scholes is the foundation of the derivatives market. The derivatives market is worth over $700 trillion. We need to know a little bit about this foundation model. We're going to go into data science and we'll jump into Jupyter Lab. Have another tab already set up here with everything. So there are many Black-Scholes pricing calculators out there. There's many Python libraries that do this, but we're going to do it from scratch here for ourselves. For one reason, because we want to calculate it using TensorFlow and also use NumPy, SciPy to calculate it, because depending on the hardware platform we're using, we're going to see some great increases in processing times and great decreases in processing times, which is even better. In that way, we can process hundreds or thousands, tens of thousands of calculations for the portfolios. So let's start with one thing. We're going to use the Yahoo Finance module, use our old friend from data science, pandas and NumPy, and we're going to use requests. We need to do some daytime manipulations. We're going to get the risk-free rate. We get the 10-year treasury yield, and this is important for properly evaluating what we're going to do. We're going to get to know this thing called FRED, which is the Federal Reserve data supplier. You have to have your API key in this request, so we're just going to type in 0.02 as the risk-free rate. To get better values, we have to have the exact data here. Here's our function to fetch the option data, and it's going to go to Yahoo Finance. It gets the expiration date, near the money call options here, and these are call options. We have a separate script over here to do the puts, because if we separate the puts and calls, we can really step through this carefully because we want to understand how this thing works. We get the options data, the stock price, the strike price, the time to maturity, the risk-free rate, which we got from the Federal Reserve today, the implied volatility, the options price. It's going to bring all that in here. There's a date and time, and we say Apple, and here's our options data, real-world options data. I did this a couple weeks ago now, on the 3rd of March, and this option expired on the 7th of March. We're going to go through hundreds of these, folks, so don't worry if you're not understanding this at all. Here in this section, we compute the Black-Scholes prices and the Greeks using the TensorFlow library here. Here's our continuous distribution function that normalizes the data, and here's where the sausage gets made. This is the implementation of how we're going to calculate the gammas and the vegas and the theta. We don't do that in this. We do it a little bit later though. So here we go, and we've just copied this over. We don't have any of this automated yet. We want to make sure this thing works, okay? Here's our Black-Scholes model results. Here's the price of the option there. We have our delta, gamma, and beta, and we're going to go through in detail what each of these does. Critically important. We looked at sigma, which is not calculated here in the last video because we want to calculate our volatility. Here we compute Black-Scholes with and find the Greeks using NumPy. And you step through here, that is the magic code, D1 and D2. And down here we actually print the comparison of the calculations between TensorFlow and SciPy, and you'll see that TensorFlow and SciPy are pretty close here, way down here at the end. There's a little bit of difference there, and the deltas here, exact same. These are gammas the same, and a little bit of difference on the vega, and lo and behold, I didn't define theta, and it conked out on us, so some improvement there. Over here on the puts, again, here it goes out and fetches the data, and this is going to give us the price for our market put price. This is the cost of our option there. We're going to learn about options. We're going to know Black-Scholes really well, and we're going to do the Greeks. Thanks for your time.